This video is another in the series for Math 1133 for UTSA. Today we're going to be talking about 13.2 integration by substitution. So this might be a somewhat shorter video. There's a handful of examples that we're going to do. Conceptually, this is fairly complicated, but in practice, when you go to solve a problem, it's not that difficult usually. Depends on the problem, of course. On the left here, we've got this example, or this antiderivative, the antiderivative of x to the fourth dx. And we know how to deal with this because we have the power rule for the antiderivative. I can say, oh, well, this is going to be 1/5 x to the fifth plus c, right? Just use the power rule. This example, however, is a little more complicated. I have a parentheses, and I have something inside the parentheses, and then I have a fourth power. Of course, over here, I could have slapped some parentheses on there if I wanted to. And notice that if that were the case, then the thing inside the parentheses is identical with the differential that I have. And we'll talk about a little bit more about the differential in a minute. But over on this side, the thing in the parentheses is not identical with the differential. So I don't have somehow like 2dx minus 1 or the differential of 2x minus 1. I just have dx. So I can't just do the power rule. This is not 1/5 times 2x minus 1 in parentheses to the fifth power. It's not. So what I have to do is the following. I'm going to identify the inside with another variable. I'm going to say that u equals 2x minus 1. Okay, and I'm going to utilize this this identification to get something that looks more like this simpler problem. So we're going to do something that we haven't done before. It might seem a little weird. In the first example, I'm just going to show how to do it, and then we'll talk a little bit about what's going on after we just show doing it. So there's a couple ways to write this next part, and I'm going to choose one in particular. So think back to the related rates problems where we would find the derivative with respect to time. I'm going to think about doing that. And I'm saying this with some hesitation in my voice because technically that's not what's really happening, but it will get us the result that we need. And you'll see what I mean. Okay. So on the left, we're just going to have du dt, right? And on the right, well, I'm going to have the derivative of the inside, or rather what's inside the brackets, but this is an outside function. X is implied to be some function of t, right, under the related rates concept. So I'm going to have 2, because that's the derivative, times dx dt. 2 times dx dt, as though this were a related rates problem, okay? And that's what you would do. Now, this is not a related rates problem, so I'm just going to get rid of the dt's. So what I have is du equals 2 dx, okay? And notice that this 2 is just the derivative with respect to x of the function. And if I wanted to at this point, I could divide dx on both sides. Okay, so then the dx's on the right would cancel, and I would have du dx equals 2. Which, of course, it does. If you just find the derivative of this equation with respect to x, right, du dx would be 2. But what we're going to be doing is utilizing this phase of this process. We're not going to use the derivative because we could have done that anyway. I want to utilize this because this will allow me to change dx into something, a differential with respect to u rather than with respect to x. Okay, so it's sort of a long-winded way of saying I need the derivative of the inside in order to switch over the differential, okay? There's a couple ways to move forward from here. So one way is to take this equation and then divide by 2 on both sides. So I think in this case we'll do that. So 1/2 du equals dx. As per usual, there's more than one way to do this, and I'm choosing to do the one that I think is more straightforward looking, although there is another method that we'll use later. So I'm going to replace the dx minus 1 with u, because that's what I said it was, right? And then I'm going to replace the dx with 1/2 du, okay? So this is the integral of u to the 4th power times 1/2 du. And so I've switched over to the variable u instead of the variable x. And now this 1/2 I can put in front if I want. I don't have to do that, but I might as well. And I now have essentially achieved this easier problem, right? The letters are different. I have u instead of x, but it's the same format, the same thing's going on. So now I can use the power rule for the antiderivative. So this equals 1/2 times 1/5 times u to the 5th plus c. Okay. Now I'm not quite done because u is something that I made up to help solve the problem. So I have to replace the 2x minus 1 back into that for my final answer. So this will be 1/10 times 2x minus 1 to the 5th power plus c. Okay? And that's basically it. And if that all made sense, then you now understand integration by substitution. That's the concept. That's all there is to it. There's other variations. Some problems are a little bit harder than others, and we'll do more examples. But conceptually, that's basically it. So one thing I want you to think about is when we apply the chain rule, I may not have mentioned that basically, well, the previous video I did mention, but so far in this one I might not have, that running the chain rule backwards is what integration by substitution is. So think about applying the chain rule. If I have something like d dx of, I don't know, let's say e to the 2x power, right? This will be e to the 2x times 2 because that's the derivative of the exponent, right? And we saw previously that the antiderivative of e to the 2x dx, we had a formula for this, and I didn't justify it in the same way that we did with the substitution, but we'll do one like that later. I'm going to have e to the 2x times 1 over 2. So in the chain rule, you multiply by the derivative of the inside function. In integration by substitution, you end up dividing by the derivative of the inside function, okay? Because that's because the antiderivative is the reverse process of the derivative. So if in the chain rule, the chain rule for the derivative, you multiply by the derivative of the inside function, then in the chain rule for the antiderivative, it would make sense to divide by the derivative of the inside function. There's technical problems with saying that we're dividing by 2, but that's sort of what we're doing. And in particular, over here, I divided this 2 to get it on the other side. So I literally divided by du dx to get it on the other side. We're not necessarily always going to do that, but that is what I wrote. I did divide that. Anyway, this is sort of a side note to connect this more closely with the chain rule. So something that might have come up in your mind, and maybe prior to this as well, maybe in the previous video. What is dx? What is it doing? Why is it there? Where does it go? Because you'll notice in oops, I want to get rid of that. You'll notice in this example, the dx is not present in the next step, right? Why does it leave and where does it go is a decent question. So let's talk a little bit about what dx is, and we'll probably develop the idea of where it goes more after that. So what is dx? So here's a diagram that's got a lot going on. This is basically, I want you to think back to the marginal analysis problems we did, like what's marginal cost. We had a very similar diagram. And you may want to go rewatch that video. That would be the video for, I guess that would be 11.4, 11.5 if you wanted to go watch that back. Anyway, so I got a function f, okay, and I kind of made it look like a quadratic, and I have its tangent line t here. So I'm using t of x as the tangent line, or in other words, y equals t of x. And I've got an x-coordinate a marked, right? That's where the tangent line is. And then I have a plus h marked. So we've moved forward by some small horizontal amount, h for horizontal. Or moved to the right by some small horizontal amount. Well, the function has a point on it at a plus h, x equals a plus h, but also the tangent line does, and they're not the same because the function curves up and the tangent line is straight, so it doesn't curve up, right? So the height difference between this point and this point is called delta y. It's the change in y, rise over run, right? So the difference from this point up to that point is delta y, okay? The height change between this point and this point is called something else, which we'll get into. Okay, one thing I want to point out is this distance here, which I'm calling h. This is equal to delta x, the change in the x coordinate. The distance from here to here is delta x, rise over run, right? From this point to this point, the rise over run would be, I don't know why the y went away. From this point to this point, the rise over run would be delta y over delta x, right? So we could ask, what's the rise over run from this point to this point? That'd be the slope of the tangent line, right? So this distance being delta x means that a plus h, this is equal to a plus delta x. Okay, it's the same thing. I'm also going to call this dx. The differential of x is a small slice of the x coordinate. It's moving forward by a small amount, essentially. So there are some minor technical differences. Well, minor. There's some technical differences, but for our purposes, h, delta x, and dx are all the same thing. Okay, so delta x equals dx, which equals h. Those are all the same. So these three things are all the same as well. Okay, so I'm going to focus on this triangle here. If I make triangle like so, then probably gonna have to change the size of this thing. Then I have this triangle here, okay? And the rise over run for this triangle is going to be equal to that of the tangent line, right? Because the tangent line forms a hypotenuse of the triangle. So dx is the horizontal, dy is the vertical, okay? So if I make which I'm going to erase in a moment, but if I make a different triangle, and this is one that we had talked about previously when we talked about marginal cost. This red triangle, its rise over run would be delta y over delta x, right? Delta y is that height difference, and delta x is the horizontal difference. But the blue triangle, the rise over run is dy over dx, and it's really a fraction. It's not just dy dx, the derivative notation. It's dy divided by dx. It's rise over run. Okay, so rise over run equals the slope, right? Just call that m, I suppose. So dy over dx, and again, it's really a fraction. It's not just the derivative notation, equals, well, this slope of this line, m, equals f prime of x. It's the derivative of the function, or f prime of a, if I want to do it that way. But I'll just say f prime of x. X is equal to a in this diagram. So this equals f prime of x. This might make sense that, well, dy dx is the derivative, so it equals f prime of x. Sure, that makes sense. But again, this left-hand side is not just the derivative, it's the rise over run for that blue triangle. So I can multiply dy on both sides. And in fact, I'm going to move this over here. So I'm going to multiply dx on both sides. So dy, being the height of that blue triangle, or the altitude of it, I guess, equals f prime of x times dx. So when you have a function y equals f of x, and you have a horizontal amount that's just some horizontal amount here, so that you're making a triangle under the tangent line, the product of the derivative with that horizontal amount is the vertical amount, dy. It's a small vertical change in the function value, but you're following the tangent line instead of the function value itself. And dy, as we talked about previously with marginal cost, dy is approximately equal to delta y. They're not the same, but they're pretty close to each other. So basically, when we use a differential to modify an integral, we're switching variables, and we're using the derivative of the function. In the previous example, that was u equals 2x minus 1. The derivative of that function gives us the ratio between the differentials. Okay. Now that ratio is not always a number. It could be a function itself, right? So if you have a quadratic, the derivative of the quadratic, what we're going to call substitution, u equals some quadratic, 2x squared minus 1. Well, then the slope is not just 2 all the time. It would depend on what x coordinate are we at. That would affect the slope. So I want to find the differential of y, given that y equals ln of x. So basically, what I'm doing is if I have the natural logarithm function, which, something like that, right? What I'm doing is saying, okay, at this point in time, what is the ratio between the rise and the run from one point to the next? That's essentially what we're asking, okay? And it's the derivative, right? So dy equals the derivative of the function, so 1 over x, times dx. And again, this is entirely because of this formula right here. dy equals the derivative times dx, okay? And if you had some other letters, like when you have u equals 2x minus 1, well, then du equals the derivative of the function times dx. Basically, the differential of the output variable equals the derivative of the function times the differential of the input variable. That's always going to be the case regardless of what letters you're using. Okay. So that's the differential. So if we had an integral involving the natural logarithm, we might need to use this differential in order to resolve that, potentially. So just very straightforward example, we're just going to do a couple where we're just finding the differential. So for this one, dy equals, well, the derivative of the function. So 9x squared plus 1 times dx. I need parentheses because, again, this is literally a product. I have something times something. If I don't have those parentheses, like so, then this says 6x squared plus, and then separately 1 times dx, which is not what I want. I want the group times dx. Okay, so again, that's it for this example. I just wanted to do a couple of differentials. Calculate a couple of differentials. I'm sorry, and by the way, if you were at a specific x coordinate, like x equals 2, then you can say, oh, well, now I can say that dy equals, what would that be? If x equals 2, then dy equals 25 dx. So the ratio between dy and dx would be 25. So the rise is 25 times as much as the run at x equals 2. And of course, when you move to x equals 3, then it will be different. Okay, so here's our first example where, the first example was, 2x minus 1 to the 4th power, but our first example after talking about the differential a little bit more. So I want to find the antiderivative of x over 2x squared plus 5. And while there sort of is a quotient rule for antiderivatives, that's in the section that we're skipping, 13.3. You can't just say, oh, well, I have u over v. Let me use a formula. It's a bit different from that. In this case, though, I noticed that the numerator is linear, the denominator is quadratic. So the bottom is 1 degree greater than the top. So what I'm going to do is I'm going to use a substitution. Some people will call this U substitution because they use the letter U all the time, but you can use whatever letter you want. You can use U, V, W, A, B, C. It doesn't matter. So I'm going to say that U, which we'll use for a few examples, but we'll use a different letter at some point, equals 2x squared plus 5. And I'm doing that because I'm thinking about what's under the fraction, the denominator. You won't always use the denominator. You don't necessarily have to. It depends. But when I see a rational function like this, let me try the denominator first. So du, the differential, well, that's going to be the derivative of this function. So 4x dx. Okay. Now, one way to go forward is to take this equation and solve for dx, and then dx can get plugged in there. I'm going to do things slightly differently, though. That's okay to do, and if that makes sense to you, the way I did the first one, You can do that. There are some technical issues with doing it that way that come up in a later section. Um, Maybe for this one, I'll show both ways, just so you see both. What's technically more correct is to borrow what you need to get 4x dx to show up here. So the x I'll put with the dx, but I need a 4 as well. So I'm going to have the integral 1 over 2x squared plus 5 times, and I need to have 4x dx. But you can't just put a 4 there and just go forward because it's not the same integrand anymore. So I need to put a 1/4 out in front to compensate. So I'm borrowing the 4, okay, and then 1/4 out front compensates. So now I have, right here, I have u on bottom, and here I have du. So I'll switch over to the other variable at this point, and I'll switch. I don't want to have u and x mixed together in the same integral, so I'm going to switch everything at the same time. So 1/4 integral 1 over u du. Okay. And now this is a more straightforward antiderivative that we have a formula for, essentially. So this equals 1/4 times the natural logarithm of the absolute value of u plus c. Okay. Now, as before, I'm not done. U is something I made up to help solve the problem, so I have to plug 2x squared plus 5 back in. So this equals 1/4 times the natural logarithm of the absolute value of 2x squared plus 5 plus c. And there's my answer. There is a little bit more than I can do, and you might have noticed this, but perhaps not. This inside function, 2x squared plus 5, is always positive. It can't be negative. It can't be 0. Because if you take a number and square it, the result can't be negative, right? And you double that, but then you add 5. So this can't be less than 5. There's no way to get 4 as a result, and there's no way to get certainly 0 or -1 or negative whatever. So those absolute value bars are actually redundant in this case. When your substitution is a function that's never negative, never 0, and you end up with absolute value bars, because that's the formula, right? The antiderivative of 1 over u would be ln of the absolute value of u. But when your u is a function like this one, you can go without them. And basically, on a written test, I would take either one. They're both fine. On online homework, probably they would both be accepted. On a multiple choice test, probably the bottom one being, well, these are sort of redundant. They don't need to be there, right? So on a multiple choice test, probably they wouldn't. So I wouldn't want you to see this and go, oh, that can't be right. Where's the absolute value bars? Well, in this case, you don't need them. Anyway, there's our I guess, second example of doing an integration by substitution. Let's do another one. So I'm going to do a substitution, and it's not always clear what substitution to do, but I noticed that this guy out in front is the derivative of this guy. So I'm thinking, okay, if I were to say u equals x squared, when I find the differential, 2x will come out of that. And I have a 2x, so that's good. So if you notice that one component is the derivative or is proportional to the derivative of another component, that second component might be what you need to substitute. So I'm going to say, let's use a different letter. Let's say v equals x squared. Okay, so dv equals 2x dx. And again, if I want, I could take this equation, divide 2x on both sides, get dx by itself, and then I can substitute into here. But since 2x is already there, and I'm not going to need to borrow, it maybe makes more sense just to do the following. Just rearrange the order and say, okay, well, this is e to the x squared power times 2x dx. And then I have v in the exponent and dv gathered here. So I can switch over to the other variable. So the integral of e to the v times dv. Okay, and that of course is not a hard antiderivative, e to the v plus c, and then I can put x squared back in. So e to the x squared power plus c. Okay. Another one that I typically look at and I don't think I have here, is the following. If you had something like this, let's say this, e to the x squared power dx, and there's no 2x in front. Like if I had an x without the 2, I could borrow 2, right, and just stick a 1/2 out in front. That would be fine. I can't just borrow an x. I can't go, okay, I'm going to borrow an x and put a 1 over x out here and put an x here. In fact, put a 2 and then put a 2. You can't borrow a variable. You can borrow a whole number or a fraction if you want. You can borrow a number, but you can't borrow a variable. So substitution really just does not help you with this one. So this, we'll say, is difficult. There are ways to get around this one. There are ways to deal with it if you needed to calculate an integral or an antiderivative like this, but they're beyond the scope of this course. In particular, this one, which is a little bit different, and you might notice that the only difference is I made the exponent negative. This one's considerably easier, but it's still pretty difficult. Okay, but more manageable. But that still beyond the scope of this course. This is something that would be handled in Cal 3, so beyond the scope of this course. Anyway, what's next? Okay, we have an application problem. So basically, integration by substitution allows us to deal with antiderivatives that are more complicated than we would otherwise be able to deal with. Kind of like when we were doing the chain rule for the derivative, it enabled us to deal with a lot more different functions than just power rule, product rule, sum rule, so forth, quotient rule. So in a future video, we will have we'll have a whole video on applications of integrals. We're just not there yet, but I want to have some application problems as we go along. So basically, this is what's called an initial value problem. We did an example in the previous class, but we'll do this one we couldn't do then because we didn't have integration by substitution at the time. So the rate of expenditure in US dollars per year to maintain some machine is m of t equals 2t plus 8 times the square root of t squared plus 8t, where t is in years. The total cost through the 4th year is $540. Okay. So A says find the total maintenance cost function. Basically, since this is the rate of expenditure, then the antiderivative would be the expenditure. Okay. So this is something we've talked about before. If you have a function, it tells you some quantity that changes over time, and you find the derivative, that gives you the rate of change as a function of time. How does it change each month or each year or whatever? So if you're given a function that gives you the rate, you find the antiderivative to get a function that just gives you the quantity. Okay, so I want, for part A, I want the antiderivative of that. So I'm going to say big M of t. This will equal the antiderivative of little m of t, which, kind of running out of room here, but that's going to be 2t, I keep saying 2t plus 8 times the square root of t squared plus 8t dt. Yeah, okay. So I noticed that this guy in front is the derivative of this guy in the radicand. Usually if you have a radical, the inside of the radical, whatever that is, the radicand, that'll be your inside function typically. So let's say v equals t squared plus 8t. So dv equals, what's the derivative? 2t plus 8, conveniently, dt. Okay, so I don't need to borrow anything. I just need to group this with the dt. So this equals antiderivative, and I'm going to rewrite this as a with an exponent rather than a root. So t squared plus 8t to the 1/2 power times 2t plus 8 dt. So I have v here in parentheses, and then I have dv here at the end. So this equals the integral of v to the 1/2 power times dv. Okay, so that's a relatively straightforward antiderivative at this point because I just use the power rule. I add 1 to the exponent and then divide by that exponent. So this will be v to the 3/2 power over 3/2. plus c. And of course, when you divide by a fraction, that's equivalent to multiplying by the reciprocal. So I'm going to do that. And I'm also going to replace v, put t squared plus 8t back in. So this equals 2/3 times t squared plus 8t to the 3/2 power plus c. Okay, so there is my maintenance cost function. Now, from this, I don't know what c is. What I have to do is use this value that I'm given. Um, this is an initial value in that you have a starting point from the 4th year, but this is not when t equals 0. This is when t equals 4. When t equals 4, then the cost would be 540. So basically, I can write that over here. M of 4 equals 540. So 540 equals 2/3 times 4 squared plus 8 times 4 to the 3/2 power plus c. Okay, so I'm going to multiply both sides by 2/3, I guess, or just subtract this whole group on both sides. So 500 minus 2/3 times, so is that 48? 4 squared plus 32, 48? Yeah, I think so. To the 3/2 power, which is going to be kind of a messy number because that does not have a nice clean square root. So this equals c. So c is approximately, we could reduce this by hand, but just go to a decimal value. 500 minus 2/3 times 48 to the 3/2 power. I get 278.297. Ah, nope, 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 nope. I wrote 500, not 540. There we go, 318. Well, I guess my decimals are all correct. 318.297. Good. Okay. So my cost function, or my maintenance cost function, is m of t equals 2/3 times t squared plus 8t to the 3/2 power plus c. No, plus c, sorry. Plus 318.297. Okay. And that's rounded, but whatever, close enough. And this is in dollars. So in fact, we could round more, but we'll leave it as it is because this is 7/10 of a penny, but we'll leave. That's fine. 3 places is pretty good. So part B said, how many years must pass before total cost, I should probably say the total cost, reaches 4,000? Okay, so when is this 4,000? We could start plugging in numbers until we get to 4,000, but maybe I want to just set this equal to 4,000 and solve that way. So 4,000 equals 2/3 times t squared plus 8 plus 8t, the 3/2 power, plus 318.297. So I'll start by subtracting 318.297 on both sides. So 4,000 minus 318.297. And I'm not going to do the arithmetic as I go along. I'm just going to type that all into a calculator at some point. And in fact, I'll probably, so of course the calculator kept a longer decimal version of this. I'll let the calculator handle that as well. Okay, so I'm going to multiply both sides by 3/2. So 3/2 times 4,000 minus 318.297, which is a lot of writing, but that's fine. Times t squared plus 8t, the 3/2 power. So I'm going to raise both sides to the 2/3 power, or apply an exponent of 2/3 to both sides. Okay, so I just realized at this point, there's something we can do that'll be simpler in some ways. So, of course, this is a quadratic equation. Just use quadratic formula. That'll be fine. But I have an 8 here. So that suggests to me something that you might not have seen in a while. I'm going to add 16 to both sides. Basically, I take the 8, cut it in half to make 4, and square that to make 16. Why am I doing that? Well, on the right, this now factors as t plus 4 squared. Okay, so I've got 16. In fact, let me go ahead and turn this into a decimal. So 16 plus parentheses 3 over 2 times parentheses 4,000 minus the 318, which I'll have the calculator keep its long form of that. 16 plus 328.435, which might be correct. I might have to correct that. I'm gonna do this again just to make sure. Okay, so 4,000 minus the 318 times 1.5 raised to the 2/3 power plus 16. Yeah, 328.435. That should be correct. Okay. So now I can apply the square root function to both sides. And I get a plus minus on the left, right? When you move the square root, or when you move the square from the right to the left, it becomes a square root, you get a plus minus, because t plus 4 could be negative, right? And then I'll subtract 4 on both sides. Okay, so I get 2 values, but of course we're going to use the plus one. You don't have negative time, right? You buy this machine and you are maintaining it. Time goes forward, not backward, right? So t is approximately -4 plus that square root. So -4 plus square root 328. I get 14.123. Okay, so basically, in the 15th year is when you reach 4,000. So cost reaches 4,000 in the 15th year, because 14 years have already passed, right? And the question is worded as how many years must pass? So the answer is 14. Okay, that's how many whole years. So 14 years pass. So there's an application problem. We'll do more later. Of we're gonna have some examples that are more specific. Basically, so in economics, we'll have some specific applications. So here's what you can do with an antiderivative. But I wanted to have some as we went along as well. Okay, what's next? All right, so just some more antiderivatives. So this one might look really complicated. There's actually, I want to say, at least 2 ways to do this one. So you could do a substitution, but it might not be obvious what to do. So you could try doing a substitution, saying, okay, u equals x, right? So then du equals dx. So you'd then have the integral u root u du, and nothing changed, right? So having a root on its own doesn't necessarily mean that you need a substitution. So let's not do that. Let's instead do the following. Let's notice that x to the square root of x is x to the 1/2 power. Okay, and this x has an implied exponent of 1. So this is the integral or antiderivative of x to the 3/2 power, because I can add the exponents. And then I just use the power rule. So 2/5 x to the 5/2 power. Let's see. No substitution needed. So just having a root doesn't mean you need a substitution. In our next example, though, we do. Because if I write this as x times x plus 1 to the 1/2 power, the bases are different and I can't combine them. right? I'm sort of stuck with that. So in the radicand, I have something that's not just x, I have x plus 1. So that's going to be my substitution. So u equals x plus 1. And again, I could use v or w or whatever letter I want. So then du equals, well, the derivative of x plus 1 is 1. So this equals 1 times dx, or just dx. So it can be unclear what to do because this is u and this is du, but what about x? What does that become? So why don't you pause the video and think about it for a minute. What would you replace x with? Okay, so what I need to do is take this equation and subtract 1 on both sides, so that x equals u minus 1. That's what I'll replace x with. So this is the integral of u minus 1 times the square root of u du. And this might not seem like it helped, but what happened is the thing inside the root is just a variable now. It's not u plus anything, it's just u. So I can write this as the integral of u minus 1 times u to the 1/2 power du. And then I can distribute this u to the 1/2 onto these two terms. This is the integral of u to the 3/2 power minus u to the 1/2 power du. So this will be 2/5 u to the 5/2 power minus 2/3 u to the 3/2 power plus c. And as before, I can't just leave the u in there. It's not part of my answer. U is something I made up to help solve the problem. So 2/5 times x plus 1 to the 5/2 power minus 2/3 times x plus 1 to the 3/2 power plus c. So that's, a minor change. That plus 1 really makes this problem a lot different from this one. You can see a similar kind of thing happened. We still had that 2/5 present, but that plus 1 made a big difference in how the problem went overall.